Hello guys, how are you today? Let's start. Before we begin though, I would like to remind you that in the previous video on the composition of matter, I have uploaded in the description the link of a file with solved questions, solved problems, maybe questions, and you should go and check them for practice. Okay? In this video, I won't upload something like that because I have questions in the video. Alright, let's get right into it. First of all, we're going to talk about the atomic structure. First of all, let's go through a historical development of the atom. I don't believe you should know the names and the dates, but I believe that through a historical development we can understand the current, the modern atomic model. I want to tell you before I begin that this is a difficult video, even for me to make, because these concepts are not that easy and you can't really imagine them. So I'm going to mention things that I will describe and explain later. So if you listen to a term and you don't know it, don't panic. Just wait for the video to finish, and if you still don't know the term, just comment below and I will help you explain that or something like that. Okay, now let's get going. First of all, John Dalton in 1808 he explained, he was the first one to introduce the term atom, although atom was a term from Democritus back in ancient Greece, when he said the word atom means a, which is a negative syllable, and tom, which comes from the word temnin, which is cut. And atom is supposed to be something that cannot be cut. It's the fundamental particle of all matter. But we now know that it is cut and we've got subatomic particles, but this name has still stayed. So what he said that the tiny invisible particles of an element are called atom. He said that atom is what makes up all the structures around us, and the structure around us, they're made up of elements. And what makes elements different are the atoms. So different elements have different atoms, and same elements, the same element has the same atom configuration. Then in 1897, J.J. Thompson came and he said that no, we don't have only atoms, there are things inside the electron which are called subatomic particles. And he discovered the existence of the first one, the electron, by using magnetic and electrical fields. Then Robert Millican was able to measure the charge of the electron with the oil drop experiment, and from that he was able to calculate the mass of the electron. And then Thompson proposed this atomic model since he saw the existence of the first subatomic particle, the Raisin-Padding model. He said that atom is a sphere of positive charge with negative electrons embedded in them. This is a sphere and the electrons are in them. All right. And then Ernest Rutherford, he came in with an experiment. What he did was that he shot alpha particles in a gold foil, in a thin gold foil. Most of the particles passed through with no deflection here. A few were slightly deflected here, and every once in a while an alpha particle was deflected back towards the alpha source, here or here. Rutherford concluded from this scattering experiment that the atom was mostly empty space, where the electrons were, and that there was a dense core of positive charge at the center of the atom that contained most of the atom's mass. He called the dense core the nucleus. And now let's look at the subatomic particles. We've got three of them. We got protons, electrons, and neutrons. Okay, the modern atomic model dictates that the atom is an electrically neutral sphere with a tiny nucleus in the center that holds the positively charged protons and the neutral charged electrons, and that the negatively charged electrons, they move around the nucleus not in circular paths. We have abandoned this belief that this is the atomic structure. The nucleus here in the center, and in circular path we got the electrons. No, this is no longer reality. The modern atomic model says that now the electrons, the negatively charged electrons, they move around the nucleus in complex paths, randomly. We don't know how electrons move. This is for quantum physicists to discover it yet, why electrons move the way they do. But we know that they move in certain areas around the nucleus, which they are called electron clouds, and there are areas of probability. Here. The electron cloud is an area of probability. Let me show you one area of, let me show you that one, that shape. You see the two lobes shape. This is an electron cloud, and what it shows us that this is where there is the higher probability that the electron may exist. Of course, 1 in the million, I don't know. An electron may be found here, or here, or here. But the electron cloud dictates that usually, 9 out of 10 cases, the electron will be found in an area inside here. We don't know why, we don't know how it moves in here, just randomly. Really, really quickly, it moves. Okay. And this is the electron cloud, or the orbital. Alright, and this is what the modern atomic model tells us. That we cannot know, we cannot say for sure where the electron is found. And actually, there is another theory, another principle, I would say, that says that we cannot specifically say at the same time the electron's place and speed, velocity. And he said that if we are able to determine with accuracy its speed, we cannot know where it is. And reverse, if we can accurately find where it is, we cannot know its speed. Alright, this is a principle that exists. Now let me move on and introduce you to the atomic mass unit, or AMU. It is used for the mass of subatomic particles and atoms. 1 AMU is 1/12 of the mass of the carbon-12 atom. Carbon-12, that means it has 6 protons and 6 neutrons. An atom is electrically neutral, we said that. But we said that it has charged particles, protons and electrons, that are positively and negatively charged. Therefore, how can it be electrically neutral? Because the number of electrons is equals to the number of electrons, and electrons and protons equal to the number of protons, and electrons and protons have the same charge, but negative and positive. Okay. Now isotopes. I've talked about them in my biology, in biochemistry videos, and we have talked about radioactive isotopes as well, so I'm only mentioning them here. We said that an element, the atoms of an element, has specific number of protons and electrons, but they may vary in the number of neutrons. So the atoms of the same element, that means they have the same number of protons, that have differing number of neutrons, are called isotopes. The atomic number is the number of protons in the nucleus. Since the atom is electrically neutral, the number of protons equals the number of electrons, and therefore the atomic number is not only the number of protons but also the number of electrons in an electrically neutral atom. The mass number shows us the sum of the number of protons and neutrons in the nucleus. And how we can determine the number of electrons, protons and neutrons. So this is the element, and we put these two symbols, A and Z, mass number and atomic number. Atomic number shows the number of electrons and protons, and A is the number of neutrons plus protons. So if I wanted to isolate the number of neutrons, I would have to subtract the number of protons from the number from the mass number. Therefore, mass number minus the number of protons, which is Z, gives me the number of neutrons. Okay. Now let's look into electron cells, subcells, and orbitals. We will try now to explain where electrons can be. Where are they? They are in various energy levels that are located in different distances from the nucleus. The lower the number of cells, the closer to the nucleus the electrons are found. So we start numbering the cells from the nucleus and below. Within the cell energy level, the electrons are grouped in subcells with slightly different energies. The number associated with the cell is equal to the number of subcells found at that energy level. I don't want you to know that, because we will see how we can say about the subcells, how we can find them. Okay. Now the subcells are denoted by the symbols S, P, D, and F. They correspond to differently shaped volumes of space in which the probability of finding the electrons is high. The electrons in a particular subcell may be distributed among volumes of space of equal energies, called orbitals, and only 2 electrons may occupy one orbital, and we will see why later. So the cell energy has certain subcells with certain orbitals. Okay. We are going to understand this table, the cells, the subcells, the number of orbitals, and the electron capacity through quantum numbers. Let's see what are those. We have 4 of them. First of all, the N number, the principal quantum numbers. It determines the size of the electron clouds. Orbitals with the same N number make up a cell. So we've got electron cells K, L, M, N. K has a quantum number of 1, L 2, M 3, and N 4. So it takes value from 1 and above. Then we've got a second number, the L number, or as it's called azimuthal quantum number, or angular quantum number, or orbital angular number. It determines the shape of the electron cloud. And orbitals with the same N and L number make up one subcell. The L takes value from 0 until n minus 1. So let's say the electron cell K, how many subcells it has? K is 1, therefore from 0 till n1 minus 1, 0. Only 1, with L equals 0. So the subcell with L equals 0 is called S, so it has only one, the S. The L with N equals 2 has the N equals 2, 2 minus 1, 1. So it has a 0 and a 1. So the subcell, the cell 2, has 2 subcells, the S with L equals 0 and the 1 with L equals 1, and so on. Now, the magnetic quantum number, ML, determines the orientation of the electron cloud in relation to the 3 axes in the space. For each value of the ML number, there is one orbital, and it takes value from minus L to L. So, if I tell you that I'm talking about the P orbital, we saw in the previous slide that the P has a value of L equals 1. How many subcells we've got? Minus L, minus 1, 0, and 1. Therefore, we've got 3 possible orientations from the subcell P. Okay, we've got PZ, we've got PX, and PY. That means that the P is oriented at the Z axis, at the X axis, and at the Y axis. Okay. And last, we've got the spin projection quantum number. You see, the spin, if you know by physics, is like a speed that shows us in which direction a particle, a molecule, something, an object, revolves around one. So it can be positive 1 second, 1/2, or negative. So we've got two possible values for the ms. If it is positive, we say it has an upward spin, and it is shown like that. It means that it travels that direction. And if it is negative, we say it's a downward speed, and it travels in that direction. Okay, so it shows us with what, how it travels around the nucleus. Okay, and now let's conclude what we said. We've got first the n number, which shows us the cell. Can be K, L, M, N. The L number, which determines the subcell, can be S, P, D, F. We've got ML, shows us the orbital, the exact orbital, which is PZ or PY or 3PY. That means on the cell 3, the subcell P, and the orbital that has an orientation on the y-axis. And the electron spin, it's positive or negative. So we usually describe an electron by the following group of quantum numbers into parentheses, in that specific order. You see here. So, for n equals 1, I can have only how many? 0 L, because L goes to n minus 1, and ML 0. So I got only the orbital 1, L equals 0 is the S. Okay, so I got the orbital 1s. For n equals 2, the L takes two values, zeros and 1. 0 is the orbital S, and 1, P. So in the cell 2, I have how many orbitals? 1, the 2s, and 3 P's. 2p x, 2p y, 2p z. Therefore, 3 P's, 3 times 2p orbitals, and 1 times 2s orbital. Therefore, in total, I got 4 orbitals. Alright, we're going to solve some exercises in order to better understand this. I know it's a bit tricky, it's difficult. Let me show you another table. We've got the principal number, so that's the energy level. It takes value from 1 and above. We've got the L number that takes 0, the S, P, 1, D, 2. The ML, the magnetic, orbital subtypes, values between minus L and plus L. Alright, and the spin which takes the positive or the negative value of 1 over 2. And now let's see the shapes of the orbitals. The orbitals said, what orbitals we've got? We've got the S orbitals, we've got the P orbitals, we've got the D and the F orbitals. Okay, that means for L equals 0, we've got the S orbital. For L equals 1, we've got the P orbitals. For L equals 2, we've got the D orbitals. And for L equals 3, we've got the F orbital. We're going to look at the orbitals of S and P. D and F are out of the scope of IMAT. It's my belief. The S orbitals have a spherical shape. And we said that the L number determines what? The shape of the orbital. So the S orbitals with L equals 0 determines a spherical shape. But we said the cell number determines the size of the orbital. Therefore, the 1s will be smaller than 2s, which will be smaller than 3s. And we said that the ML determines the orientation. The ML for the L equals 0 is 0. So it determines no orientation because it is spherical. It does not have an orientation across an axis. But let's go and look at the p orbitals. The p orbitals have an L equals 1. That means that the ML number, which takes value between minus L and L, takes the values minus 1, 0, and plus 1. So we've got 3 p orbitals across the 3 axes. The p orbital shape, which is determined by the L, is an hourglass with 2 lobes. This is the shape. So, the px orbital is in that way. The py orbital is oriented that way around the nucleus, and the z orbital is oriented that way in space around the nucleus. Now, if this is the nucleus, we see that the electron has a very small probability to be found across the nucleus. In contrast to here, look how high the probability found near the nucleus is. Okay. And now let's do some exercises in order to see whether we have understood what I've said. First of all, which of the three orbitals below are 1s, 2s, 2pz, 3px, and 3s? First of all, let's find out the s's. I've got 1s, 2s, and 3s. Okay, I remember that the s orbitals have a spherical shape. So first of all, I'm going to see which have a spherical shape. A, delta, and E. Okay, so A, delta, and D have a spherical shape. Now we choose 1s, 2s, and 3s. We said that the number here, the n, determines the size. So the smaller this one, the smaller it. Therefore, this is the smaller, that should be 1s. This is a bit larger, this is the 2s therefore, and this is the most large, therefore this is the 3, the 3s. It's the 3 because it's the largest, and s because it has a spherical shape. And now we're below 2pz and 3px. Now I don't expect you to know the x's, but the 2p, of course these are the p's because they have the two lobe shape. Alright, so these are the p's. The 2p will be smaller than the 3p, therefore this is the 2pz, and this is the z-axis, and this is the 3px, and this is the x-axis. Alright, let's look at another exercise. An electron belongs in the orbital 3px. Which of the following group of quantum numbers has 3px? Alright, so let me write them down and then we will match with what? We said that in parentheses we put n, then we put l, then we put m, l, and then we put ms. Of course, I cannot know the ms number because, why? Why I cannot know the ms? Because I cannot know if it has a positive or negative spin. One of the ones will be. The n number is the 3. Alright. Then the orbital is the p. Therefore, p equals to l equals to what? 1. Right? And the ml, the x. I don't expect you to remember that, although some teachers do. But here, the option is obviously, because the only number started with 3 and 1 is this one. Alright, and actually, the ml for the px is 1. And this could be either plus 1 over 2 or negative 1 over 2, but this is the option that matches the 3p orbital. Where is that so? First of all, this is not even possible, because the L must be smaller than the L. Therefore, this is not even possible. What is this depicting? 3, the 2 is D, and then I don't expect you to know the rest. What is this depicting? 3, the 0 is the S. So this is showing the 3s orbital. So we see that the subcell 3 has 2s orbitals. Why? Because it has 0, 0, plus 1 over 2 and minus 1 over 2. No, actually this is an exercise later, so I'm doing that later. What are the symbols of the orbitals determined by the following quantum numbers? Interesting. Let's look at it. 2. L equals 1 shows me the p orbital. And ml equals minus 1. If you go to the slide before, well, I showed you that. ml minus 1, it shows me the y. Therefore, 2py. Okay? Then, 3, L0, therefore, L for 0 is the s orbital, and ml0, s orbital does not have any orientation, therefore 3s. And then N4, 4, L equals 1 is the p orbital, and ml equals 1 is the x orbital, therefore 4px. Alright? Now, which of the following groups of quantum numbers are possible and which are not? Let's go through the first one. Is this possible? What is this depicting? 1, that means 1, 2, 0, s. The ml is, of course, 0 because the ml takes values between the L and the minus L. Therefore, if the L is 0, the ml must be 0. Therefore, this is acceptable. Yes, this is a possible one. 1, 1, 1. The n number is 1, the L number is 1. This is a problem because we said here that the L number takes values smaller than the n until n minus 1. Therefore, we cannot have 1, 1. 1, 1 cannot exist. This is not acceptable. This is 2. The n number is 2, the L is 0, acceptable, and this is the ml, again 0, of course acceptable. Alright, and it is depicting the 2s with an upward spin. Alright, let's look at this. 2, the n, the L 1, it's smaller than 2, okay, and the ml minus 1. Is that possible? Let's remember the values that ml takes. ml takes values between L and minus L. That means that if L is 1, ml can take the values minus 1, 0, and 1. Therefore, this is possible. Let's look at that now. 2. N is 2, L is 0, and L is 1. Let's remember this relationship. Alright. If the ml is 0, then the L... No, if the L is 0, then the ml is between 0 and 0. Therefore, it can only be 0. The ml must be 0. The only value it takes for the s is 0, because we said the s orbital does not have an orientation. Therefore, this is not possible. And now let's look at the last one. 3, the n is 3, the L is 2. L must be smaller than n, therefore 2 is possible. Minus 2, it is, so for L equals 2, ml can take values minus 2, minus 1, 0, 1, and plus 2. Therefore, minus 2 is an option, and minus 1 second, of course, it is an option. And this is an acceptable one. Now, let's just write the 4 quantum numbers of each electron that corresponds to a full 3p orbital. Let's now look at a 3p orbital, how many electrons it can have with, let's see the same, let's make the groups. First of all, the 3p has an n equals 3 and L 1. P has L1. Alright, ml can take values between minus L and L, therefore the ml takes the values 1, 0, 1. So I start my parentheses with first of all 3 and 1. Okay. Then I will put the minus 1. And the ms can take these values. Okay, 3, 1. I start with the minus 1. Minus 1 can take 2 ms numbers, plus 1 over 2 or minus 1 over 2. Okay. Now, I'm trying the 1, the 0. 3, 1, 0, and the ms can take positive or minus. And then I'm taking the ml1, 3, 1, 1, plus 1 over 2, and no, I'm sorry, oh my god, this is a terrible mistake. This is negative 1 over 2. Okay, so the 3p orbital can have 1, 2, 3, 4, 5, 6 electrons. We said that the 3p has 3 orbitals in 3 orientations. Therefore, this is the 1, this is 1, and this is 1. And as we can see, Each orbital can have two orientations, plus 1/2 or -2. Therefore, it can have an upward spin or a downward spin. Upward spin, downward spin, and downward spin, upward spin, and downward spin. And this is a full, let me write that down, 3px, 3px, 3py, and 3pz. Alright, this is a full 3p orbital. It has how many? 1, 2, 3 orbitals. It is a 3p subcell actually. Yes, it is a 3p subcell. It has 3 orbitals here. Okay, this is all for this video, guys. I know it's quite difficult. If you have any textbook, you should consult it along this video. If you have any questions, please feel free to either email me or comment below. You don't have scientific questions according to my videos, and I don't know if that's good. That means you either understand it all or you either understand nothing. And it's a bit terrifying, to be honest. But anyway, that's all for today, guys. Thank you for watching. Bye bye.